guys, it's me Kirsten, and today's video is on Le Chatelier's principle.
So let me introduce you to a very important person in the history of chemistry. Here we have Henri-Louis Le Chatelier. He was an influential chemist and engineer. He was a member of the Academy of Science, the Royal Swedish Academy of Science. Those are the people that give out the Nobel Prizes. He was chair of inorganic chemistry at the Collège de France, professor at the Sorbonne, Knight Grand Officer of the Legion of Honor. That's the greatest honor that the government of France gives. He was pretty busy, this guy. Here's what he said. Look, when a system at equilibrium is subject to a change in concentration, temperature, volume, or pressure, the system readjusts itself to partially counteract the effect of the applied change, and a new equilibrium is established. Let's see how this idea works in chemical systems. Here's the reaction between sulfur dioxide and oxygen gases, making sulfur trioxide and releasing 197 kilojoules of energy. What happens if we were to have an equilibrium system like this one and increase the oxygen concentration? The concentration would go up, the forward rate would increase and use up some of that oxygen, and when a new equilibrium was established, you'd have more oxygen than before. Of course, the sulfur dioxide would be used up in that process, and at the new equilibrium, you would have less sulfur dioxide than before. Now to the product side, you would see the forward reaction having sped up, made more of the products, and you would have a new, greater concentration of sulfur trioxide. We would say this system shifted to the right and made more products at the new equilibrium. How about if we were to decrease the sulfur dioxide concentration? Well, it would go down, the reverse reaction would continue, and make some more of it. So at the new equilibrium, you'd have less sulfur dioxide than before. The new equilibrium, you'd have more oxygen gas than before. Remember, the reverse reaction had kept on going to make more of it. And of course, the sulfur trioxide concentration would be down because the reverse reaction had continued. This reaction shifted to the left. Adding heat, or increasing the temperature, would certainly cause the endothermic side, the right-hand side of the reaction, to go faster and use up some of that sulfur trioxide. On the left-hand side, you'd see that you had more sulfur dioxide made after the increase in its temperature and also more oxygen gas. So at the new equilibrium, you would have more of these reactants and less products, and we would say this reaction had shifted to the left. How about if we were to decrease the volume of the system? Well, instantly, of course, the concentrations would all jump up. Remember, what is concentration except number of particles per unit volume? But you can see that the decreased volume would favor the side with the fewer particles, and we would say that this reaction had again shifted to the right. Okay, there was more products afterwards than before. Here's his principle again. The idea that a change in concentration, temperature, or pressure shifts the equilibrium to minimize the change. This reaction here, the nitrogen and hydrogen combining to make ammonia, let's just balance that here. This one here releases 92 kilojoules. It's a very important problem in the history of chemical synthesis. We call this the Haber process now. Notice that the nitrogen molecule here has this difficult bond to break, this triple bonded nitrogen. So we use a catalyst, usually iron, to help do that. To make ammonia, we would want high concentrations of nitrogen and hydrogen. We'll have to keep adding those to force reaction to the right. Also, we would want low concentrations of ammonia, so we'll have to remove that to draw the reaction to the right. We'd also like to have high pressure to squeeze those four particles in the left together. And minding out that the reaction is exothermic, we need a high enough temperature to keep it going and the catalyst active without favoring the reverse reaction too much. So unfortunately, Le Chatelier himself in 1901, he was onto the right combination of conditions, but a small amount of air contaminated his apparatus. A huge explosion resulted, sending fragments of the apparatus through the floor and ceiling, nearly killing his assistants. Le Chatelier gave up on the project, and 5 years later it was finally perfected by Fritz Haber and his compatriot Claude. We really can't overestimate the value of Le Chatelier's principle, and if you were to forget everything else you learned in this course, please let Le Chatelier's principle be the noteworthy exception. The idea that when stressed, equilibrium systems respond in such a way to counteract the effects of the imposed stresses. So that's about it. Have a look at the next two videos in this playlist for more, and stay tuned for our next lesson in Chemistry 12, Lesson 9, the Equilibrium Constant.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!